Great, so let's get rolling on this. So here's again this the system that we spoke about that we want to try and solve now. And now let's look at how we can solve a statically linearly overdetermined system equation. Okay, almost said statically overdetermined, but a linearly overdetermined system equation. And why is it linearly overdetermined? Just remind ourselves again, we've got 6 equations we need to satisfy, but we only have 3 variables. So the reality is, we can't really solve this. There is no solution to this problem in general, okay? There might be a solution if some of these equations contain the same information, so they're linearly dependent, as well as on the right-hand sides. But in general, there will be conflicts. I can only choose A, B, and C in such a way that there will be some difference. But what I want to try and do is to say, okay, maybe we want to try and get this difference as small as possible. So think of this matrix here. We're going to call it A. This A, B, and C's we'll call Z. And this right-hand side vector we'll call V. Okay. So in general, the best we can do is to say A times Z will only be approximately equal to V. Okay. But because we can't solve it exactly, doesn't mean we can't do a good job. Okay. So what we can do at least and say is, okay, A to Z, let's take it to this side, minus V. We want to get as close as possible to 0. That's maybe a good thing, because if I choose Z such that this difference is 1,000,000 versus if I choose Z that this difference is only 10, we can argue that then the 10 difference is better, yeah? And what I mean with that is, with 1,000,000 and 10, this is a system of equations. So imagine if I've taken some norm to get to the 1,000,000 after I've taken the difference, or I've dotted this with itself and say that if I take this difference, that's a vector, and if I dot that vector with itself, it's a scalar, and if that scalar is then 1,000,000 versus that scalar is it's 10. Okay, so that's essentially what we can ask. And we can definitely argue that the 10 is a better solution than the 1,000,000. So as long as it's different, the closer we get it to 0, the better job we do, essentially. And all that we do is to say, okay, well, what we can do is, this difference can be positive or negative. Okay, so let's first say, let's just get this into a quantity that is always positive. And the smallest it can be is 0, and that is if it's exactly satisfied. So what I'm going to do is I'm going to just say, take this AZ minus the V, okay, transpose, I dot it with itself, because this is just a vector. What you see here is just a vector. Matrix times a vector is a vector minus a vector. Okay, so that's essentially all we see here. And I'll make sure I don't go off the board there. And I want to say, let's try and get this as close as possible to 0. But what we know is that this expression cannot be negative. It can be at best 0, and that is if AZ equals V, then that will be 0. Otherwise, it will be some positive value. Okay, so that's the base what we can essentially do. And now what we can say is this we can call sort of an error. Yeah. Error as a function of Z. That is what we can call it as. And that's really what I've just written down here. Okay. Now what I wanted to say is we can now formally minimize this, or we can go back to our sort of our high school maths and remember that, okay, we can maybe, if we know the function is sort of nice and quadratic and nice and convex like this, if I want to try and find the minimum of this function in sort of the 1D case, and I know it's got this shape, okay, so I know that this is some quantity that's always going to be positive, at best 0. So it will have this kind of shape as well. So what it's, if you think of this as sort of the variable Z in the 1D case, and this is sort of our error as a function of Z, what we know is that at best it can maybe be 0, if that even exists. But in general, there'll be maybe a minimum, but it will be some offset, it will be some positive value there. But it's essentially, as I go, if I choose different Z's, I might get an error that's larger or smaller, but it will have this kind of convex shape. This is what I know about this. If I want to find the minimum of this, well, from high school maths, from sort of grade 10 maths, we know that we just have to find the derivative of this with respect to Z to be equal to 0. So we can say, if we find the spot where the derivative of dE with respect to Z is equal to 0, oops, let me just make sure I write properly. I just want to mention, if I write Z, I do it like this. This is unfortunately a bit of a German influence, but that's the way I write Z. So take note that this means Z. Okay, it's not a crazy symbol. This is just Z. Okay. So essentially, let me just rewrite this. This is a very poor job. So what I want to say is dE dZ is equal to 0. Okay. If I find that point, I know I found the minimum. Okay. And I don't even have to check now for the second derivative to be positive, because that's what we would typically do at school, because I know the shape of this function is nice and convex. So I know the second derivative of this thing is positive. Okay, that's great. So let's work with that kind of assumption, and let's see, can we find this? So what we need to do to find that is to say, let's maybe first just expand this whole thing out. And let's write all the terms out properly. Okay, so let's just make sure I start here on the, so I can start here. That's perfect. And then say, so if I take the transpose of AZ transpose, I swap the order, and then I write the transposes, so it's Z transpose A transpose minus V transpose, okay? So this is going to have to multiply with this now. Okay, what I'm going to do is I'm going to just write this minus V transpose at the bottom here, and say, let's take this term here, which is this transpose, and multiply it with each of these terms. So this will give me then Z transpose A transpose times A Z. And then this times this will be minus, so it will be Z transpose A transpose minus V. Okay, and then on this side I've got V transpose. So it's negative V transpose multiplied by AZ, and then essentially negative V transpose times V. But it's a negative V, so that will become a positive. And that must be equal to 0, approximately equal to 0, as far as we can. Okay, we want to try and at least solve that as close as possible to 0. So these are the terms that we have, and now I can say, let's take the derivative. Let's take the gradient of E, Z with respect to variable Z. And so now that we work with matrices and vectors, we just have to make sure that when we write things down, that we write them maybe always as a column vector. So that's all I'm going to keep track of. Otherwise, we start mixing column and row vectors, and then we can't add them properly. So this is really all that we're going to have to take care of. And so I'm going to just ask every time, is this a column or a row vector or not? Okay, so let's take the derivative of this term. First off, we can take the derivative with respect to Z transpose, and then I'll get A transpose A Z. Okay, that's what remains if I take the derivative of this. If I take the derivative of the same expression with respect to Z, if I do this version, I'll end up with, if I write it as Z transpose A, it becomes a row vector. If I take each transpose, it will become A transpose A Z. It will be the same term. So essentially, I can write this same term twice, 2 times this term. And you can think of this Z transpose Z with the matrix inside. It's almost like an AX squared in 1D case, but the A transpose A in the order is quite important. But the first term, the derivative of this, A transpose AZ, I know is a column vector, because this is just a matrix times a vector. That's a nice column vector. And if I were to take the derivative with respect to this, and I think to write this down, I will end up with a row vector. But if I take this thing's transpose, I swap the orders. So it will become A transpose A Z. It will be exactly the same term. Okay, and we can essentially just move forward and say here, if I take the transpose with respect to Z transpose A transpose V, if I take that derivative, I end up with minus A transpose V. And then we can get to this term. But before I continue, I just maybe want to remind you what this is just a scalar. Okay, maybe I should have made that more explicit. It's clear that it's a scalar because I've taken the dot product of the vector with itself. But I just want to remind you, this is a scalar term, this is a scalar term, this is a scalar term, and this is a scalar term. This is just a vector dotted with itself, which is a scalar. Okay, so I just want to make it so loud and clear that it can't be confused. If we take the derivative of this with respect to Z, I end up with V transpose A, which is again a row vector. If I take its transpose, it's A transpose V, which is this 2 times. Okay, so that's essentially, that's 2, it looks terrible every time. What am I doing? Okay, that's essentially what I have there. If I look at this, V transpose V, that's just a constant, so its derivative with respect to Z is just falls away to 0. And this is essentially, we want to try and say, this now is the gradient of E, and this we want to set equal to 0. So this E, we want to try and get as close as possible to 0. But now that we've taken the gradient of E with respect to Z, we want to say this expression needs to be exactly equal to 0. This is now a gradient vector. That's why I'm going to put this bar at the bottom. So I'll just, again, put the double bar, single bar, just to remind you what's vectors and stuff. It's easier to see. So this is the expression that I want to try and solve to be equal to 0. So all I can say is the 2's will cancel out. I can divide by 2, and I can move this towards the side. And what I have is then A transpose A Z is equal to A transpose V. Okay. And that's essentially what we have, what I've just written down here for you at the bottom. Just to make sure that you understand the derivation. It's no rocket science, basic optimization. It's really an extension of our grade 10 mathematics in terms of optimization that we get here. But what I can tell you is, and maybe I'll just pause here for a second, because I want to stop the video and then I'll do this continuous one as a separate video. What I do want to just mention is that what you're seeing here with this system of equations that is overdetermined, and these variables here that you see here and this right hand side, so make sure I find it, this right hand side, with lots of things that we want it to be equal to. This idea is just called regression. So we are regressing essentially the best quadratic through the data. And this is really the bread and butter of almost all machine learning on the planet today. This is what's making lots of money for lots of companies. So Facebook, Google, all of these companies have a lot of what they're doing at the moment in terms of data science is built on this simple idea of solving overdetermined system of equations. That's as simple as that. To say that I know that I can't find an exact solution, but I can find sort of a good solution. And if I do it properly, I can sort of find provably the best solution. And this is what we've done here. Okay, but take note, this discrete approach, we're not going to continue on further in this course. I'm just doing it so that I can relate it back to something you've seen before in linear algebra. But also just to remind you that this is really something that you can take further. And this is one of the courses that I present in the postgrad courses, the MOOC course, the Optimum Design course, really takes this and solves this with some steroids and stuff like that, extending this kind of solutions to these kinds of problems quite a lot. So that's a large focus of what we do. Then this is really the bread and butter of a lot of the data sciences. But in this course for MKM, we're really going to be focusing on this continuum approach. And in the next video, I'm going to say, let's quickly see how we would go about solving our error term that we want to try and minimize using the continuum approach, so that we can go and do that derivation. Okay, so hopefully this will get you excited about where we're heading. And also just to note that although we're doing this, we're not extending on this. It's good that you see it, because it's a good reminder, especially if you want to start fitting functions in MOX next year or in MRN, in your research project. This is really something that you should maybe consider revisiting at that stage. Okay, good day. I'll see you.